Basically, the elements contain n which satisfy these both conditions. It should be between 10 and 100, both inclusive, and 3 raised to n minus 3 should be a multiple of 7. So let's try to understand solution. First, let's build some momentum for this question. Let's understand what the question is saying. The first condition is quite clear, right? It has to be between 10 and 100. And it can attain 10, 100 both. Not an issue, right? The problem lies in the second condition, where we need to analyze in little bit of detail. 3 raised to n minus 3 should be a multiple of 7. Now, whenever we say something is a multiple of something, let's say we are saying if x is a multiple of 3, then x is equal to 3 into something, right? Obviously. If we are saying x is a multiple of 3, what we mean by it is we can write x equal to 3 into something something, right? So here 3 raised to n minus 3 is a multiple of 7. This information is given to us. What we can do is we basically can write this 3 raised to n minus 3 is equal to 7 into something, right? So we wrote 3 raised to n minus 3 is equal to 17 for some integer k, right? We need not care about k. Can do anything. We just need a 7 and it is there, right? And you can now rearrange this expression 3 raised to n minus 3 as this. It is the same expression, right? Because when you multiply 3 here, it is 3 raised to n minus 3, which is the LHS. What we need here is we need this expression to be a multiple of 7. Okay. Now let's understand how to analyze this. So let's explore a few powers of 3 modulo 7. What does modulo mean? Modulo just means the remainder when you divide by 7. Okay. So when you say 3 raised to 1, it's 3 mod 7. Why? Because when you divide 3 raised to 1, which is 3, by 7, you get remainder as 3. Similarly, when you divide 9 by 7, you get remainder as 2. 27 by 7, you get remainder as 6. So this is what the meaning of modulo is. 3 raised to 1 is 3 raised to 1 leaves 3 as a remainder. 3 square leaves 2 as a remainder. 3 cube leaves 6. 3 raised to 4 leaves 4. 3 raised to 5 leaves 5. And 3 raised to 6 leaves 1. Now when you see for 3 raised to 7, the remainder will start repeating from here. Okay. And so we can say 3 raised to n mod 7, it follows a cycle of 6, length 6, right? Because after every 6 powers, the remainders repeat. Similarly, we can say if 3 raised to n mod 7 follows a cycle of length 6, similarly 3 raised to n minus 1 mod 7 also should follow the same cycle. But of course, it should be a little shifted because why? 3 raised to n minus 1 is 3 raised to n divided by 3. So there we are dividing by an extra 3. So it should follow the same cycle, but it would be a little shifted. So we can clearly say, let's say if it is 3 raised to 0, okay. So it would be 1 mod 7 clearly, right? Obviously. If 3 raised to 1 is there, then it would leave 3 mod 7. 3 square would leave 2, 3 raised to 3 would leave 6, as we can see from here also. 3 raised to 4 would leave 4, 3 raised to 5 would leave 5. And the cycle will start repeating from here on. What we wanted is, we wanted this expression to be a multiple of 7. So if this is a multiple of 7, then it should leave 0 when we divide by 7. It should leave the remainder as 0 when we divide by 7, obviously, right? So here the condition is written that it is leaving 0 mod 7. This also means, now see, 3 into 3 raised to n minus 1 we are writing, right? 3 is obviously not a multiple of 7. And still, if it is leaving 0 as a remainder, when we divide by 7, this means what? 3 raised to n minus 1 should also be 0 mod 7, right? This should leave the remainder 0. And from the cycle above which we analyzed, right, n minus 1 should be a multiple of 6 because the cycle repeats after every 6 elements, and we saw for 3 raised to n minus 1 how it behaves. So when n is 1 more than a multiple of 6, this thing will leave 0 mod 7. And we can easily find those numbers between 10 and 100. Why between 10 and 100? Because first condition clearly said n has to be between 10 and 100. When we check the numbers between 10 and 100 which satisfy this condition, we will get these many numbers. And now we need to add 1. Why? Because see, n is 1 more than a multiple of 6. So we add 1 to all these values to get the numbers. And we can get 15 numbers in this. So the answer to this question becomes 15. Okay. Let's move on to another question. I hope this is clear. This is a fairly simple question, but it was asked this year only. Okay. We have defined a set A which contains minus 4, minus 3, minus 2, 0, 1, 3, and 4. And we have defined a relation R which contains A comma B, which belongs to A cross A. The condition is that B should be mod A or B square is equal to A plus 1. So if an element A comma B satisfies either of these two conditions, then we will include it in the relation. The minimum number of elements that must be added to the relation R so that it becomes reflexive and symmetric is. So that's what we needed. Okay. We need just the minimum number of elements that must be added to the relation R so that it becomes reflexive and symmetric. First of all, we need to understand which elements R contains right now. Without adding the number of elements, we will first analyze what are the elements which are initially there in R. So when we analyze them, we will see that these elements are there. Why? Because in every element, you will see B is equal to mod A, right? You will see that. Oh, sorry, in every element, you will see either one of these conditions holding true. So in first one, you will see mod B is equal to A. In second one, in second one, you will see that mod B is equal to A. B is equal to mod A, my bad. So B is equal to mod A in both. Similarly, it holds here also. It here holds here also, here also, here also. Here it holds what? B square equal to A plus 1, right? Here it holds B square equal to A plus 1. Here, here B is not equal to mod A, but B square equal to A plus 1. So we see every element either holds this condition or this condition. Now what we see here is all the elements are not reflexive, right? What I'm saying is R is not yet reflexive. What we need to do is to make it reflexive. We have seen a definition of reflexive relations. A comma A should belong to reflect relation for all dam A, which is belonging to capital A. So for every element in this, there should be A comma A in relation. And what we need to do is we have to find the minimum number of elements that must be added so that it becomes reflexive and symmetric both. Not only reflexive, but we need to see about symmetric too. So for symmetricity, what we need to do is if A comma B is in R, then B comma A should also be in R for all A comma B belongs to capital A. So first of all, let's see about reflexive. We clearly can see minus 4 comma minus 4 is not there. Minus 3 comma minus 3 is not there. Minus 2 comma minus 2 is not there. We need to add these elements so that it becomes reflexive. We didn't add 0 comma 0 because it is already there. 1 comma 1 was already there. 3 comma 3 was already there. 4 comma 4 was already there. Right? Some reflexive elements were needed and so we added them. For it to be symmetric, we are adding some more elements 4 comma minus 4, 3 comma minus 3, 1 comma 0, and minus 2 comma 3. These elements, of course, should be added so that it can be made symmetric. Why? Because minus 4 comma 4 was there, but 4 comma minus 4 was not there. So we added that. Minus 3 comma 3 was there, but 3 comma minus 3 was not there. So we added that. Right? We are adding these elements. So we can see that minimum number of elements which we have added 3 plus 4, which is 7. Now, why are we saying it as minimum? We are saying it as minimum because we can add more elements to it to make it reflexive and symmetric. But we just need to what we need to do is we have the existing elements already, and we just need to add some elements so that those elements satisfy the conditions, right? When we add these elements, we are seeing the initial elements and we are adding accordingly. We can add thousands of elements to make it to continue to be it reflexive and symmetric, right? We're adding only the required elements, minimum required elements. So that's why we said minimum number of elements. Okay, let's move on to another question. This is a quite simple one. It was asked on a fatal evening shift this year. So you're seeing the methods which is being used here to solve these questions. They are so see first question we solved, it was not straightforward at all. So during exam, if you see such a question and you do not have good confidence in solving that, you can leave it for the end. And if you have time, you can come back to this question and solve it. But do not try to waste 10-15 minutes in a single question. Now you can see this is a fairly simple question where a set A is given, which contains elements from 1 to 7, and relation R is defined such that x plus y is 7. Okay, the relation R is defined on set A. Whenever I say a relation R is defined on set A, it means R is basically A cross A. That's it. And some condition is being imposed on it. Okay. Now we see we need to like eliminate. We need to find the correct answer from these four answers options. Okay. So if you see, it's given that x plus y is equal to 7. Okay. So for every x which we take, y has to be 7 minus x. If we are taking x equal to 1, y is 6. X equal to 2, y is 5. X equal to 3, y is 4. X equal to 4, y is 3. X equal to 5, y is 2. And x equal to 6, y is 1. All these elements satisfy this condition. So we manually founded these elements. And now we apply these three properties of equivalence relation to find it. First, let's apply symmetric one. For every element here, you can see that if A comma B belongs to R, then B comma A is belonging to R, right? Why? Because 1 comma 6 is there. Similarly, 6 comma 1 is there. 2 comma 5, 5 comma 2. 3 comma 4, 4 comma 3. So it is clearly symmetric. Now let's check for reflexive. 1 is there, but 1 comma 1 is not there. So element A is there, but A comma A is not there for any A belonging to capital A, right? Clearly, it's not reflexive. But let's now check about transitive. A comma B belongs to R and B comma C belongs to R. For it to be transitive, A comma C should belong to R. Let's check any two elements. Let's say 1 comma 6. 1 comma 6 belongs to R, 6 comma 1 belongs to R, but 1 comma 1 does not belong to R. So it is also not transitive. Okay. Hence, C option is correct because it's only symmetric, not transitive or reflexive. Now let's see another PYQ which was asked this year in 29th January evening shift. This is a good question. Let R be a relation defined on capital N as A R B, A relation B, if 2A plus 3B is a multiple of 5, A comma B belongs to natural numbers, then R is. Right? 2A plus 3B should be a multiple of 5. That's what the condition is. We need to find the elements. So we need to check these conditions on R. Okay. So let's analyze all the properties one by one. Let's analyze reflexive first. So 2A plus 3B, I told you in the first question. Let's go back to first question. Here 3 raised to n minus 3 was a multiple of 7. For anything to be a multiple of 7, that anything can be represented as 7 into something, right? Here also, if 2A plus 3B is a multiple of 5, then 2A plus 3B can be written as 5 into something. That something we have taken here is m. Okay, so 2A plus 3B is equal to 5m. For reflexivity, we are putting a comma a here. If we put 2A plus 3A, it becomes 5a, right? So 2A plus 3A is 5a. So which is a multiple of 5, right? So a comma a belongs to this relation because 2A plus 3A, it's a multiple of 5 clearly. So this relation is reflexive. Now let's check if it is symmetric or not. So we are putting a comma b in R. So see, we had 2A plus 3B is equal to 5m, right? Now we clearly know we can say that this is obviously true in general because 5 is there, 5 is there. So this 5a plus b can be represented as a multiple of 5. This 5a plus 5b is broken down into these parts. This, as you can see, it's just 5a plus 5b. And here 2a plus 3b is there, which is a multiple of 5. Hence, 3a plus 2b also has to be multiple of 5, right? Why? Because when you take 2a plus 3b over onto the right side, the full RHS is a multiple of 5. So LHS also has to be multiple of 5. And hence, b comma a also belongs. Because why? When you put b comma a in this, 2a plus 3b is equal to 5m. We get 3a plus 2b is equal to 5 into some multiple, right? So clearly the relation is also symmetric. Now let's check for transitive, if it is transitive or not. So as we know, if a comma b belongs to R and b comma c, then a comma c should belong. Let's check if it is not, if it is true or not. So 2a plus 3b is 5n, 2b plus 3c is 5n. Here m and n are some random things. We just want to denote. We have just written it so that we can show that it is multiple of 5. Okay. Now we are just adding these two equations and we get 2a plus 5b plus 3c. 5b is a multiple of 5. We will take it to the right side. This is m plus n, sorry guys. This is m plus n minus b. And as you can see, 2a plus 3c is also a multiple of 5. That means a comma c belongs, a comma c is also multiple of 5. 2a plus 3c is also multiple of 5. That means a comma c belongs to R. So it proves that if a comma b belongs to R, b comma c belongs to R, then a comma c also belongs to R. Hence R is transitive. And since the relation is reflexive, symmetric, transitive, all three, hence it is an equivalence relation. Okay, hence A option is correct. Hence option A is correct. Okay, because it is both It is all three: reflexive, transitive, and symmetric. Let's move on to the last question for the day. It's also a similar question, but little bit more twisted. Okay, so this question could take more time during exam. So you need to allocate your time perfectly to be able to solve this. For alpha belongs to natural numbers. We are considering a relation R on capital N, which is given by R containing x comma y. 3x plus alpha y is a multiple of 7, right? This condition is there. 3x plus alpha y should be a multiple of 7. And this relation should be an equivalence relation if and only if. Okay, it's a single correct answer. So one option is correct. Only one option among these four should contain the condition that makes this relation an equivalence relation. Okay, so let's start analyzing this question now. So, okay, for it to be an equivalence relation, first of all, it has to be a symmetric relation. It has to be reflexive. It has to be transitive. Let's start with reflexive. Okay, A comma A belongs to R for all A belongs to N, right? Obviously, since the relation R is on N, we see elements in N. If A belongs to N, A comma A should belongs to R. We are putting A comma A in this, we get 3A plus alpha A, right? So which is nothing but this plus 7. It's just the same thing, right? So reflexive condition we have seen. Let's move on to symmetric. Now we can always use alpha equal to 7k1 minus 3 because this has to be true, right? So if A comma B belongs to R, then B comma A should belong to R. What we are doing now is we are putting first of all A comma B. So if we put this, we get 3A plus alpha B. Alpha we are writing as 7k minus 3 here. So 3A plus 7k minus 3 into B, which is equal to 7m. Now we are rearranging this. This is 3A minus 3B plus 7KB is equal to 7m. And if we now replace A by B, that is, if you want to see if B comma A belongs to R or not, we are replacing it here. So this becomes 3 into B minus A plus 7KA is equal to 7m. So we can clearly see that this condition is getting hold. 3x plus alpha y is a multiple of 7. because we can rearrange this to get this just A and B interchanged and still holding true. So it is symmetric also for alpha equal to 7k1 minus 3. Now we will check for transitiveness. We defined A comma B belongs to R, B comma C belongs to R. We, we will put it in the expression. We will get these two expressions. We will add these two to get this. We will take the 7kb on the right side because it is also a multiple of 7. We will get this. And this expression, you can relate it by seeing this one. It clearly says that A comma C also belongs to this relation, right? So it is also transitive. So we see that if alpha is 7k1 minus 3, then it satisfies all the three conditions. That is transitive, reflexive, and symmetric. All three are holding true. So that's what we wanted. And hence we can say rewrote this alpha as 7k1 plus 4, and it's the same thing which the D option says. That is 4 is the remainder when alpha is divided by 7, which indeed it is, right? So yeah, D option is correct. So I hope each one of you have understood these questions in great detail because I've tried to explain all the concepts through these 4 5 PYQs. And so yeah, that's it for today. Thank you very much.